Okay, seems as if my live is up and running. So let me go to the PowerPoint slide. Let me minimize this. Oops. Okay, so in this chapter, as you can see on the screen, we'll be focusing on gases, their properties, their behaviors, and how we can explain them, all right? So let's talk about what gases are like. And if you look at things at the microscopic level, you'll see that gases are basically small particles which are widely spaced and they're always moving, right? So if you can visualize this, you'll see that basically the particles are always moving, but on average, they are far from each other as possible. As a result of what we just described, this imparts certain properties to gases. They tend to flow readily and they tend to spread to occupy the entire volume of their container. Now, you from time to time may see or hear the term vapor, which is basically a gas that is normally a liquid at room temperature and pressure. So we tend to use the term vapor in reference to such substances such as water or methanol vapor. But when it comes to gases that exist as gases under normal room temperature, and pressure conditions, then basically it's gaseous is a term that we would associate with it. So oxygen, for example, and hydrogen are examples of gases. So therefore, we would not use the term vapor when it comes to such substances. And in terms of the substances that tend to behave as, or substances that has the term vapor associated with them, these are substances that tend to have low molar masses and therefore can easily vaporize into gases. And the examples, as I mentioned before, are water and methanol, and there are others as well. Okay, so these are just some examples of gases, common gases and their uses. And just to highlight a couple of them, ammonia can be used to manufacture plastics and fertilizers. Chlorine is a disinfectant and a bleach. Nitrogen is used in the manufacture of the ammonia that we mentioned up here. And of course, oxygen, our very lives depend on it because we need it to respire. And of course, it can be used to support combustion. So these are all examples of gases. And they'll be the focus of what we were talking about today. So the theory that is used to explain the behavior of gases is called the Kinetic-Molecular theory, or KMT for short. And this is a model that is used to describe how gas particles behave and how that's translated into the properties that we observe, all right? So the basic assumptions of this theory is that the particles are in rapid random motion, and the movement of these particles through three-dimensional space is called translational motion. There are other modes of, by the way, other modes of motion that gas particles will undergo. You have translational, you have rotational, and you have vibrational when it comes to molecules. Okay, so if you understand all these here in terms of describing how particles behave in a gas, then you can relate it to, for example, the fact that gas exerts pressure on the walls of the container that they're located in. And this is as a result of the continuous collision of the gas particles with the wall of the container. So because of the continuous bombardment of these particles with the container walls, the net result is pressure exerted on the inner walls of the container. You can also understand the relationship between temperature and pressure based on the kinetic-molecular theory. Basically, it's more complicated than this, but basically what happens is that as you increase the temperature of a gas, you're imparting energy to the gas particles. The gas particles move faster. They will hit the walls of the container harder and with greater frequency, and therefore, as a result, exerts a greater pressure on the walls of the container, all right? Okay, so basically that's the kinetic-molecular theory, and we're going to go into the different laws later on based on this theory. And these are laws, some of them you should have met before, and I think you'll be introduced to maybe others along the way in this course. Okay, so first I want to talk about a particular property that is unique to gases, the fact that they can exert pressure, all right? Now let's define what we mean by pressure first. Pressure is basically the force exerted per unit area. So it's not just a force, it's force per unit area. And in everyday language, people tend to use the terms pressure and force as if they mean the same thing, but they're different. They're related, but different, right? Force is basically a push or pull, all right? While pressure is the force applied over a particular area. And this is the particular property of gases that we'll be focusing on here. Now, in terms of the units that force is expressed in, there are a couple. According to the SI system, force is expressed in terms of newtons per meter squared, right? Which is given the name Pascal. So the Pascal unit, abbreviated PA, is the same thing as newtons per meter squared, all right? And then you can have, of course, the application of prefixes to express larger or smaller units of pascals. The one that is more often used is kilopascals. And that's because Pascal is a small unit. So therefore, 1 kilopascal, of course, is equal to 1,000 pascals. And there are some other units that are also commonly used in science. As far as pressure is concerned, you have the atmosphere unit, all right? And then you have what is known as the millimeter mercury unit, which is the same thing as a torr unit. And I'm going to say more about the millimeter mercury unit, how that was discovered or derived later on. All right, so there are different units that we use for the expression of pressure values, and they're all related to each other, which I'm going to show you on the next page. So 1 atmosphere, which is a unit of pressure, is equal to all these here, right? Now, the ones that we'll be concerned with in this chapter will be the millimeter mercury unit, the torr unit, the newtons per meter squared, the Pascal, which is the same thing as newtons per meter squared, and the kilopascal. The others, I don't honestly anticipate us using these in any of the work that we'll be doing in this chapter, right? But these are some other units as well for the measurement of pressure, all right? Now, how do we measure pressure? Well, it depends on what you're measuring the pressure of. Now, let's say you have a gas trapped in a container and you want to measure the pressure of that gas. Well, I'm sorry, I'm jumping the gun. Suppose you want to measure the pressure of the air we breathe, the atmosphere. The air we breathe is a mixture of gases and therefore it exerts pressure. So the instrument that we use to measure the air we breathe is called the barometer, that is used to measure the atmospheric pressure. And by definition, 1 atmosphere is equal to the pressure exerted by a column of mercury exactly 760 millimeters high. We're going to explain what this means shortly. But basically for this section, we'll be concerned with these relationships, the relationship between the atmosphere unit, millimeter mercury, torr, and the kilopascal unit. So these are the relationships between these units, all right? Okay, so let's look at this setup here. We have 2 troughs filled with mercury, right? And mercury is the liquid of choice for a reason which I will get into later on, all right? But for now, just accept that mercury is the liquid of choice for this setup. Now, let's say you insert a tube into this trough of mercury and both ends of the tube are open. And what you'll see is, of course, that the mercury level here outside of the tube will be exactly at the same level as the mercury level here inside of the tube. And the reason for that, of course, is because you have the atmospheric pressure acting on the surface of the mercury outside the tube, and the atmospheric pressure is exerted inside the tube on the surface here as well. So they cancel out each other, and therefore the mercury levels will be the same inside and outside of the tube. Now, that's what happens on the left. In the case of what happens on the right, the difference is that the tube that is inserted into the mercury has one end sealed, right? So the way this is done is that before you insert the tube, you cover the mouth of the tube here and then invert it into the trough, and then you release your finger, and then the mercury moves up into the tube until it gets to a height of about 760 millimeters, right? So there's a vacuum here, we're assuming, right? And basically what happens is that the pressure that is exerted outside the tube on the surface here pushes the mercury level up here, all right, to this height. So therefore, this column here of this height exerts a pressure at this juncture here at the same level as the mercury level outside. This mercury column exerts the same pressure as the atmospheric pressure. And that's where we get the relationship between the atmosphere unit and the millimeter mercury unit. The millimeter here refers to the height of the mercury column in the tube. So therefore, that's where we get the relationship between the atmosphere unit and the millimeter mercury unit, all right? So by definition, 1 atmosphere is equal to 760 millimeter mercury, all right? So based on what we have just covered, let's see if we can do this example here. Let me choose the correct ink. Okay, so the question says that the pressure, oh, I need to plug in, let me plug in my tablet. Let me plug in my tablet. Okay, now I'm in business, I think. Hold on, let me, oh, shoot. I need to click on this again. Black ink. Okay, so the question gives us 100.2 kilopascals, and the question is asking for us to convert to torr. All right, so basically it's a simple conversion problem like we have done before. 102 kilopascals multiplied by the relationship between the kilopascal and the torr unit is that 760 torr is equal to 101.325 kilopascals. All right. Now, unfortunately, I left my calculator at home. But
here, give me a second. I've got whatever it's called. Let's see here.
Well, you're working it out?
Yeah, 100.2 times 760. Okay, let me type that out real quick. 761.
Divided by 101.
Yep.
0.325.
325. That would get set. That would be 751.5618. Which
okay, so that would be 57. That would be 751 point what?
751.5618.
Okay, so 6. All right, and this would be torr. All right, so that's basically how that is done. All right, simple conversion from kilopascals to torr based on the relationship between those two units. Okay, any questions about this example? Any questions?
Not me.
Okay, so the other instrument that is used to measure gases or measure the pressure of gases is called the manometer. Now, this is used to measure a gas that you may have trapped in a container, right? And the pressure that is measured is based on the difference between the heights of mercury or some other liquid. But mercury, again, is the liquid of choice for reasons which I'll get into later on in the two arms of the manometer, all right? So the manometer looks like this. And as you can see, one part of it, it's basically a U-shaped tube, right? One end is connected to your container with the gas, and the other end is sealed in this case. But later on, you're going to see that we can have this end open. So this is an example of what we call a closed-end manometer, all right? So if you open up the stopcock here, the gas flows through and it exerts its pressure right here. So the pressure of the gas will be exerted here. There is a vacuum here. So there's no pressure exerted by anything here. So therefore, the height difference between the two mercury levels on both sides of the U-shaped tube would be equal to the pressure of the gas, right? Whatever that would be in millimeters of mercury, right? Now, if you want to express the pressure in pascals, then this would be the equation you would use. And for those of you who have done physics or are about to do physics, you're going to meet this equation here. The pressure exerted by a column of a liquid is equal to G. Now, G is a constant known as the acceleration due to gravity. D is the density of the liquid, and H is the height, which is the same thing as the delta H right here, all right? So therefore, if you express G in meters per second squared, and the density in kilograms per meters cubed, and H is in meters, then the pressure would be expressed in pascals, all right? So that's basically how you can calculate the pressure in pascals if you want to, based on this setup right here. But usually the pressure is expressed in millimeters mercury, so therefore we basically use a ruler to measure the height difference between the mercury levels on either side of the U-shaped tube, all right? As I said before, this is what happens in the case of an open-ended manometer. But you can also have, this is a closed-end manometer. You can also have an open-end manometer, which is what is shown here, all right? So same setup, but the difference is that this end is open. And because of that difference, you can have the atmospheric pressure exerting on this surface area here on this side of the mercury, right? Now you'll notice that the atmospheric pressure here is expressed as P bar, and that's because the atmospheric pressure can be called also the barometric pressure, right? So if you hear me using the term barometric pressure, it's the same thing as atmospheric pressure, right? Now, what we see here are two different situations, right? So I'm going to deal with each of them in turn, starting with the situation here on the left. So again, as we did before, we open up this tap, the gas flows through, exerts its pressure here, and pushes the mercury such that this end moves up, right? So we can establish, based on what we have here, the relationship between the pressure of the gas and the barometric pressure. And obviously, the first thing we can notice and say is that the pressure exerted by the gas here must be greater than the pressure exerted by the atmospheric pressure, by the atmosphere here, right? So what that tells us is that the difference between the pressure of the gas here and the barometric pressure here would be the height difference between the mercury levels on either side, right? So the relationship between P gas, delta H, and P bar is that P gas is equal to the sum of the barometric pressure plus delta H, and that's the equation that is given right here. The barometric pressure plus the delta H value, which is the height difference between the mercury levels on either side, will be equal to the pressure exerted by the gas, all right? So that's basically how you can calculate the pressure of the gas based on this arrangement right here in the case of an open-ended manometer. Now on the right side, we have things flipping a bit, where the pressure exerted by the atmosphere is greater than the pressure exerted by the gas. And that difference would be equal to delta H. So therefore, in this case, the relationship here would be that the barometric pressure will be equal to the pressure exerted by the gas plus delta H, which is the equation right here, all right? So that's basically how you can establish the relationship between the pressure of the gas and the barometric pressure and the delta H value in either case, all right? Now, here's a question that's being asked. It says for part B, what is the pressure of the gas if delta H is 100 millimeters and the barometric pressure is 760 millimeters, all right? So they're talking about this part right here. So any ideas as to how you can solve this?
Would the answer be 660 millimeters mercury?
I think you're correct, because the equation you'll be using would be this equation right here, right? And the question is asking for P gas. So in this case, P gas is equal to P bar minus delta H. And P bar, let me just do it over here. P bar is equal to 760 millimeters, mercury, minus 100 millimeters mercury. And the answer, as you correctly said, is equal to 660 millimeters mercury. And that's how that is done. All right, very good. Any questions about this particular setup? Any questions about the open-end manometer?
No, not me.
Okay, now, please forgive the scribblings here. I did this while recording a video. But I want us to look at this example, and this example is very important because this example explains why mercury is the liquid of choice and not water, for example. I mean, water is less expensive, much less expensive than mercury. And therefore, based on cost, one would be, tempted to ask, okay, why don't we use water in instruments such as the manometer or the other instrument? Oh gosh, I forgot. Anyway, so this example gives you the reason why. This question says, the barometer, that's what I was trying to remember. So this question says, calculate the height of a column of water. It gives the density of water that exerts the same pressure as a column of mercury, gives the density of mercury, 760 millimeters high, right? So the first thing I would do, right, is write down this. The pressure exerted by the water column, PW, is equal to the pressure exerted by the mercury column, PHG, right? Because that's what the question says. It says the height of the water column exerts the same pressure as the column of mercury, right? So I established that first. And then, if you remember, I talked about this expression earlier. The pressure exerted by a column is equal to the height of the column times the acceleration due to gravity times the density of that liquid, right? So I would actually write this expression for each of these two terms. And that's what I did right here. Let me turn on my, and here. So that's what I did here, right? And I did a similar expression here. Okay, so basically, turning back my pointer on, the height of the water column times G times the density of water is equal to the height of the mercury column times G times the density of the mercury column, all right? And then what I did next was that I canceled G on both sides. And then what I did next was divide both sides by the density of water, because what I'm trying to obtain is the height of the water column, which is what the question is asking for, right? So when I divide both sides by dW, the density of water, these cancel out, so you're left with HW equals to H, the height of the mercury, times the density of the mercury divided by the density of the water, right? So that's the expression here. And then what I did was put the numbers in. So when I put the numbers in, 760 millimeters mercury times the density of mercury divided by the density of water, this is what I got, 10,300 millimeters, all right? So that would be the height of a water column that you would need in order for the pressure to be equal to 760 millimeters mercury, which would be the height of a mercury column. So that's the reason. What, I'm sorry?
That would be nearly 3 feet high, or over
exactly.
3 feet
It would be
high.
a very, right, exactly. You would need a tube, which would be 10.3 meters high. Just to give some idea, you said what, what did you say? You said
nearly or over 3 feet high.
Actually more than that, because my height is, I'm just under 6'5", right?
Goodness gracious.
I know that 6'5" is about 2 meters, right? So 10.3 meters would be about 3 times my height, right? So if you're going to use water instead of mercury, you're going to need a column, which would be 3 times 6'5". What is that? Whatever that height is, 18 plus 18 feet, right? Which would be very inconvenient in terms of, using an instrument. And that's the reason why mercury is a liquid of choice when it comes to measuring atmospheric pressure, because you don't need as long a tube if you're going to use mercury. And that is actually due to the fact that mercury has a relatively high density. I don't think there's any liquid that has a density as great as that of mercury, all right? So this problem explains why mercury is the liquid of choice when it comes to instruments such as the barometer or the manometer, all right? Yes, sir.
The reason people use mercury, in addition to it just being conveniently dense, would it also be that it doesn't vaporize very easily, and it's
that's a very important point.
Okay.
Because going back to this here, right? You notice I mentioned that this is a vacuum, right?
Yeah.
Now, technically speaking, that's not 100% true, because any liquid in this situation will have some vapor above, right?
Yeah.
But mercury, for some reason, well, I know the reason why, I won't go into it. Mercury emits a very, very, very small amount of vapor, right? So in effect, right here is a vacuum, right? For most intents and purposes. So you're right. That's another reason why mercury is the liquid of choice, because it does not exert what we call a vapor pressure above it. Water exerts a significant amount of vapor pressure at room temperature. So therefore, that's another reason why water would not be, I would say it's a secondary reason. The primary reason, of course, is the length of the tube required, which would be very inconvenient as an instrument. But the secondary reason is what you just mentioned, the fact that mercury has a low vapor pressure. Okay, what next? What next? What next? What next? What next? Okay, so what we're going to look at from here on to the rest of the chapter are some laws which govern the behavior of gases. And the first law we're going to look at is Boyle's law, which relates the pressure of a gas to the volume, right? And basically, in words, Boyle's law can be stated as for a fixed amount of gas at constant temperature, excuse me, the volume of the gas varies inversely with its pressure, all right? Another way of stating it is that the product of the pressure and the volume is constant for a gas of a fixed amount at a constant temperature. So these are two statements basically saying the same thing. You can also express Boyle's law mathematically, and that is P times V equal constant. The pressure times the volume is equal to constant, or P initial times V initial is equal to P final times V final, or if you're like me, I would just simply express it as P, whoops, okay, why did it jump all the way up there? P1 V1 is equal to P2 V2, all right? So that's another way of expressing Boyle's law, right? And we all know this from our everyday experience. You might not recognize it, but you know, if you take a balloon, for example, and let's say you squeeze it or try to reduce the volume, you know that the pressure will build up. That's the inverse relationship between the volume of a gas and its pressure. And we can also represent this law graphically. If you plot P on the y-axis versus V, you're going to get this smooth curve, right? And you can see how if you were to reduce the pressure, or let's say if you were to reduce the volume from 4V to 2V, then the pressure will be doubled from, in this case, 1 atmosphere to 2 atmospheres. And if you reduce the volume again from 2V to V by half, the pressure will be doubled from 2 to 4 atmospheres. So that's basically the relationship between pressure and volume. And then over here, we have the relationship between 1 over P versus volume. And this is actually a bit more convenient quantitatively because you have a linear relationship. Let me explain how this works. So basically, if you know that P, let me squeeze it down here. If you know that PV is equal to a constant, then you know that, how should I do this? You know that V will be equal to, I'm trying to see how I should, will be equal to K over P, or another way of stating this is V over K is equal to 1 over P. If 1 over P represents the Y axis and V represents the X axis, then 1 over K would be the slope. So let me rewrite this as 1 over P is equal to 1 over K times V. All right, so this would be the Y. 1 over K would be the slope. And V would be on the X axis. And that's basically the reason why you get a straight line relationship here. You get a straight line relationship here when you plot 1 over P versus V, all right? So these are just two ways of representing Boyle's law. Okay, any questions about this?
Not so far.
Okay, so let me move along. So here is an example involving Boyle's law. It says you have a helium-filled party balloon, which has a volume of 4.50 liters at sea level, and the atmospheric pressure is 748 torr. Assuming that the temperature remains constant, what will be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? So, remember the equation, or my way of expressing it is P1 V1 is equal to P2 V2. So when you get a question like this, you have to identify what the different terms are. So I would identify this as V1. I would identify this as P1. I would identify this as P2. And the question is asking V2. So basically it becomes a problem of rearranging this arithmetic, algebraically, I should say. So V2 is equal to P1 V1 over P2. Shucks. P2. Okay, I can't find my, oh, here it is. P2, all right? And then I put the numbers in. So P1 is equal to 748 torr times V1, which is equal to 4.50 liters, divided by P2, which is 557 torr. Okay, so again, I'm going to need your help since I don't have my calculator to do some number crunching here.
Sure thing.
So can somebody work this out for me?
Yeah, let's see. I guess that's 3 significant figures, so it would be 6.04 liters.
6.04 liters. That sounds correct. Okay, so that's basically how you would do a problem of this type. Now, let me just say something here concerning the use of this law here. When you're using this law, you have to make sure that the units are consistent. In other words, you have to make sure that the units for P1 and P2 are the same, and that the units for V1 and V2 are the same, all right? So for example, you could be given a problem where V1 is in, let's say, torr, and V2, I'm sorry, not torr. V1 is given in liters, and V2 is given in some other unit, let's say gallons. Then you'd have to do some conversion, right? You'd have to either convert the volume V2 into liters or convert V1 into gallons, all right, in order to make sure that the units are compatible when you put them into the problem, and then you can solve from there, all right? And the same thing is true for the pressure units, right? Both P1 and P2 have to have the same units, right? So if P1 is expressed in atmospheres, and let's say P2 is expressed in millimeters mercury, then you have to either convert the millimeters mercury to atmospheres or convert the atmospheres to millimeters mercury, all right? And then you do your subsequent calculations. So that's something that you have to be aware of when it comes to the units. It doesn't matter what the units are, as long as they're the same for each measurement on both sides, all right? Okay, any questions about this example? Any questions? Any questions?
Don't believe so.
Okay, moving along. So the next law we're going to look at is the relationship between temperature and volume, and this is Charles' law. So Charles' law, stated in words, is that the volume of a fixed amount of gas at a constant pressure is directly proportional to its Kelvin, which is also the absolute temperature. And that's very important, as you're going to see shortly. The temperature must be expressed in Kelvin. We're going to get into the reasons why that is so. So this brings about the concept of absolute zero, which is a temperature that is obtained when you extrapolate the graph. If you plot volume versus temperature and you extrapolate the graph, you'll see that the line cuts the x-axis at a particular temperature value, which is known as absolute temperature. And this represents a temperature at which the gas molecules has no kinetic energy. In other words, it has no translational energy, no rotational energy, no vibrational energy, right? And it turns out that absolute zero on the Kelvin scale is the same thing as minus 273.15 degrees Celsius. So in other words, 0 Kelvin is equal to minus 273.15 degrees Celsius. Okay, So this is the graph that I was just referring to. If you plot the volume versus the temperature in Celsius, you're going to get a straight line, all right? Now, we all know that all gases liquefy if you lower the temperature to a certain level, right? Which would be the boiling point of that particular substance. So of course, if the gas turns into a liquid, then we cannot do any more successive plots of volume versus temperature as you lower the temperature. So what was done was that they extrapolated that line for the gas to temperatures below the boiling point of the gas, and they found out that that line cuts the x-axis at the aforementioned 273.15 Kelvin, right? Which represents, of course, absolute zero, which, as I said before, is a temperature at which the gas particles will have no kinetic energy whatsoever, all right? So this is where we have the origins of the Kelvin scale, because what was decided based on this observation, that the temperature at which the line cuts the x-axis, that is now defined as 0 Kelvin, and therefore, as a result, we end up with a relationship that I showed you before, which is, let me do it down here, write it down here. Which is the temperature in Kelvin is equal to the temperature in Celsius plus 273.15, all right? And to be more accurate in terms of unit, this would be 273.15 Kelvin times hold on, wait a minute, 270. All right, let me leave that out. Just let's leave it at temperature in Kelvin is equal to TC, temperature in Celsius plus 273.15, and that would be it, right? So that's basically how you convert from Celsius to Kelvin, and that's how we end up with the Kelvin scale, all right? So as we said before, as indicated here, where it cuts the x-axis, where it cuts the x-axis, that would be 0 Kelvin by definition. Okay, so based on this, we can do this example. So this question gives you the initial temperature. Oh, one more thing I should have mentioned. Hold on 1 minute. Okay, Charles' law can be expressed mathematically. I did not mention that. And that is V1 over T1 is equal to V2 over T2. All right, that's Charles' law. And V1 and V2, of course, would be the volumes, initial and final. T1 and T2 would be the initial and final temperature, but these must be expressed in Kelvin, right? Very important. Okay, so again, if given a question like this, you have to identify the different terms, right? So this would be V1, the initial volume. I'm sorry, this would be T1, the initial temperature. The 2.0 liters would be the initial volume, and the minus 23 degrees Celsius would be the final temperature T2, right? And the question is asking for the volume outdoors, which would be V2. So basically what we have to do is rearrange this equation here to solve for V2. And that can be easily done by multiplying both sides by T2. So when you multiply both sides by T2, these will cancel out. So you'll be left with V2 is equal to T2 V1 over T1, all right? So T2 is, and we have to convert the temperatures to Kelvin. So T2 is minus 223 plus 273 Kelvin.
315.
Time,
300.15.
Okay, so 300.15. And times V1, which is 2.00 liters, all divided by T2, which is
250.15.
Okay, so this here would work out to be 200 and what? 50.15?
15.
Okay, good.
Yep.
And then you work it out. So can you work that out for me and let me know?
Sure, just give me a second. Okay, so that would work out to be it's 3 significant figures, 2.40 liters.
2.40. And the units would be liters.
Yes.
Which makes sense because if you, oh, wait a minute, something is wrong.
Yes, indeed.
Yeah,
something
that
is
don't
wrong.
make sense actually. You may need to work those numbers again. It should be higher. It should be
yeah, it makes sense. It shouldn't be higher, but it is for some reason. My math.
Let me check this. Maybe it's a setup. V1 times T2. Okay. I see the mistake. Let me erase this here. The 300.15 should be down here, and the 250.15 should be above. So.
Ooh, that makes sense. Okay, I'll adjust my equation.
I don't know. That's my fault. Let me see why I did that. Oh, well, there's no good reason I can come up with. So let me change that here. Okay, so.
An update. It's actually 1.66.
So up here, this should be 300.15, right?
Yeah. No. That should be on the bottom. Yeah, T1 is on the bottom. Okay.
Oh, okay. Hold on.
No, wait. Dang.
T2, right?
Yeah.
Is the minus 23, right? So that should be what?
Yeah, that should be that should be 250.15. Okay. Okay. 250.15.
Okay, and then below you should have what?
300.15.
Okay, all right, good. So what does that give you when you?
That works out to be 1.67 liters.
That makes more sense.
Indeed, much more.
1.67.
Yep.
Okay, so that basically is how that is done, all right? Which makes sense now because the volume is lower because, you know, the temperature is lower, all right? Okay, any questions about this example? Any questions? Any questions? Okay. The third, and I think the final law we'll be talking about is, well, maybe not the final law, is Avogadro's law. And this law describes the relationship between the mole of a gas and the volume. And in this case, it's a direct relationship. At a fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas in moles or to the number of molecules of gas. And we can write it mathematically as the volume is directly proportional to the number of moles, or the volume is equal to a constant times the number of moles, or V over N is equal to a constant, or another way of stating it, I'm going to squeeze it up here, is, come on. V1 over N1 is equal to V2 over N2, all right? So this is a convenient mathematical way of expressing Avogadro's law. Now, at this juncture, I want to, I would say, reintroduce to you, because you should have met this before, the concept of standard temperature and pressure, right? And this is important because, you know, the way gases behave, temperature and pressure, of course, affects the behavior of gases very dramatically. So if you want to make meaningful comparisons between gases, you can hold the temperature and pressure constant and vary other things so that you can, say something about, the behavior of one gas relative to another under those conditions, right? So the powers that be have decided a long time ago that standard temperature and pressure, by definition, would be 0 degrees Celsius and 1 atmosphere respectively, all right? So whenever you hear the term standard temperature and pressure, or STP, then you should immediately understand and know that the conditions that we're talking about are 0 degrees Celsius and 1 atmosphere in terms of the pressure, right? Another concept that you should have met before is the concept of the molar volume. And basically the definition of the molar volume of a gas is a volume occupied by 1 mole of the gas. And it turns out that under STP conditions, the molar volume occupied by an ideal gas is equal to 22.4 liters, right? So that is something that is true for all gases, assuming that they're ideal. And later on, we're going to talk about the difference between an ideal gas and a non-ideal gas. But for now, we're assuming that all the gases that we're dealing with are ideal gases. So for all gases, the molar volume under STP conditions is equal to 22.4 liters. Okay, so based on that fact, we can do this problem. This question says calculate the volume occupied by 4.11 kilograms of methane, and it gives you the formula at STP, right? So turn on my pen again. So basically, you're given 4.11 kilograms of methane, and you're asked to determine the volume, presumably in liters, at STP, all right? So the way I would go about this is that I would start off with the 4.11 kilograms of methane, and then I would convert this to grams. And we know that 1 kilogram of methane is equal to 1,000 grams of methane, all right? So that this unit cancels out with this unit. The next step is to convert from grams of methane to moles of methane. So we're going to have 1 mole of methane here, and down here we're going to have the grams of methane, which would be the molar mass. And of course, being the lazy person I am going to go to my trusty molar mass calculator. And I'm going to plug in the formula for methane, which is CH4. Oops, 4. Calculate, and according to this, it works out to be equal to 16.04 grams per mole. So let me go back to the PowerPoint here. Okay, so turn on my pen. So here I'm going to put 16.04. Oh, that's a different color. I don't like red. I like black. Okay, so so far we would have determined the moles of methane, but the question is not asking for the moles. The question is asking for the volume. So the next step would be a conversion factor, which allows us to convert from moles to volume. And since we know that the conditions are STP conditions, the conversion factor here will be 1 mole of methane would be equal to 22.4 liters of methane. And you work that out, right? Because here, the mole of methane will cancel out the mole of methane here. So again, I'm going to need your help. Can you work out?
Sure, I was following along with you. So altogether, that would be 5,739.651. And there's
5,700 and what?
39. And
okay, so to convert this to, to round this off, I should say, to 3 sig figs would be 5,740 liters of methane.
Wow.
Yeah.
Quite a lot.
So, Yeah, well, not surprisingly, because the mass you start off with here is quite large, 4.11 kilograms. So yeah, so that would make sense. Okay, any questions about this particular example? Any questions?
Nope.
Any questions? All righty. Okay, so we have learned 3 laws so far. And you'll notice that in each case, you'll hold 2 things constant. So it begs the question, what if everything changes? What if the volume, pressure, temperature, and the amount of gas change? Then we can combine them to form what is known as the combined gas law, which can be represented as PV over NT is equal constant, or P1V1 over N1T1 is equal to P2V2 over N2V2, right? And of course, you know, you can use this to solve problems where you're given any 7 of these terms and you're asked to find the 8th term, all right? So that's basically the combined gas law, which combines the gas laws that we just learned about, the Boyle's, the Charles, and the Avogadro's law. So based on what we have learned here, let's see if we can do this problem. I wonder if I can squeeze it into the side here, the solution. Anyway, question says that you have oxygen in this flask. Here, the conditions here would be STP, which means that the temperature is 0 degrees Celsius and the pressure exerted by the gas is 1 atmosphere. Over here, same gas, same container, but the difference is that the temperature is 100 degrees Celsius. So the question is asking, what's the pressure exerted here? Now, without doing any calculations, of course, one would come to the conclusion that the pressure exerted by the gas in the boiling water would be greater compared to the pressure exerted by the gas under 0 degrees Celsius conditions, right? So the first thing I'm going to write down is, go back to my pen here, is, let me see here, P1 V1 over N1 T1 equals to P2 V2 over N2 T2, right? T2, okay. Now the first thing I'm going to do is cancel out N1 and N2. Why? Because they're the same. It's the same amount of gas in both flasks, right? That doesn't change, right? So we're left with P1 V1 over T1 is equal to P2 V2 over T2, right? Now, the next thing I'm going to cancel out is V1 and V2. Why? Because it's the same flask, same volume. So therefore V1 is equal to V2. So therefore we are left with P1 over T1 is equal to P2 over T2. So the question now is asking for P2. So P2 would be equal to P1 T2 over T1. And then I'll just put the numbers in. So P1 is STP, which is 1.00 atmospheres times T2. Now T2 is 100 degrees Celsius, which we have to convert to Kelvin, which would be 373 Kelvin, all divided by T1, which is 273 Kelvin. Okay, so again, I'm going to need your help. Can someone work this out? Tell us what this gives.
Oh, sorry, I was muted, but I'm working on it. 273. All right, that gives us 1.37 atmospheres.
1.37 atmospheres. And that's basically how that is done, right? And again, it makes sense. 1.37 is greater than the 1 atmosphere before, which makes sense because you're changing the conditions that the temperature is higher, so therefore you'd expect the pressure to be higher as well. Okay, any questions about this example? Any questions about this example? Any questions? Okay, so let's now talk about the ideal gas law, which is, without even mentioning it before, we actually got introduced to it earlier. PV over NT is equal to a constant. Turns out that that constant has a value of 0.0821. I would just say for our purposes, we round off to 3 sig figs for that value. liters atmospheres over mole Kelvin. And please note the collection of units associated with the ideal gas constant. It's liters atmospheres over mole Kelvin. So you can express the ideal gas law this way, or more, it's more likely or more familiarly expressed this way in most textbooks, right? So this is the ideal gas law. And of course, you have to be careful about the units. So if R has this value, the pressure would have to be expressed in atmospheres, the V in volume in liters, N in moles, and T in Kelvin. Now, for other units, then the R value would be different along with the units. So that's what this table is all about. If P is expressed in torr, then R changes to this. If P is expressed in pascals and V is in meters cubed, then R is changed into this, right? Now, for most of this chapter, you'll be using this value of R, all right? But later on, you'll be using this value of R for some other calculations. So I'll let you know exactly when this value of R will be used, all right? Okay, so we can use that equation to solve a problem like this one right here. So in this case, they gave you the moles, they gave you the volume, and they gave you the temperature, and the question is asking for the pressure, right? So PV is equal to nRT. So P would be equal to nRT over V. And we put the numbers in. So the moles would be equal to 0.508 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times T, which is 303, all divided by the volume, which is 15.0 liters. So that's a setup. And please, folks, whenever you're solving problems of this type, make sure that you include the units so that you'll see the units canceling out, like what we're going to do now. The liters will cancel out here and here. Kelvin will cancel out here and here. Moles will cancel out, whoops, here and here. So you'll be left with atmospheres as your final unit. So again, I'm going to need, I'm sorry, folks. So again,
Yep, I got it.
you're going to need to calculate this. You have to round off your answer to 3 sig figs. So what's the answer here?
All right, that would be 0.842.
0.842. I'll take your word for it. Okay, so that's basically how that one is done. Any questions about this? Any questions? Any questions? Okay, I think I have another example lined up here. What is the volume occupied by 16.0 grams of ethane at 720 torr and 18 degrees Celsius? Now, this one is a bit more challenging because we have some unit conversion to achieve. In fact, tell you what, I want you to look at this question. I'm going to step away for a minute. I'll be right back. Just look at this question and think about it, and maybe you can tell me how you go about solving it, all right? So I'll be back in the next couple of minutes.
All right, so. So Mhm. Okay, let's see here. 16.0, that's 3 sig figs divided by 30.03. Okay, so 0.53 moles. Okay. PV equals RT. Okay. And convert to atmosphere. And let's see here, we want to convert Tor. 720 is equal to let's see here, 0.
Okay, folks, I'm back. So any ideas as to how you tackle this problem?
Oh, I'm getting into it. I'm just doing all my conversion factors right now.
Okay. Well, let me see here. The question is asking for the volume,
Mm-hmm.
right? The question gives you the mass of
Yep.
ethane. It gives you the formula. That's important.
Mm-hmm.
Gives you the pressure in torr, and it gives you the temperature in Celsius. So what I would do is I would try to convert, well, the formula you would use is PV is equal to nRT, right?
Mm-hmm.
And the question is asking for the volume. So in this context, the volume would be equal to nRT over P, all right? So N would be equal to, okay, so how would you get N, the number of moles? Anybody?
Oh, I'd figure the molecular weight of ethane and which happens to be 30.01.
Yeah, that sounds about right. 30,
divide 16 by that.
I'm sorry,
and
this would be 1 mole
yeah,
divided by 30.01 grams, right? That's for the ethane. So the grams cancels out and you get the moles, right?
Yep.
And then I'll multiply that by R, which is 0.0821 liters atmospheres over mole Kelvin. And then I'll multiply that by the temperature, which is 18 degrees Celsius, which you have to convert to Kelvin. So that's 273 plus 18, that gives you what?
What was, oh, the temperature is 291.
Okay, 291 Kelvin, that sounds right. And then we divide all of that by the pressure. Now they gave you the pressure as 720 torr, which you'd have to convert to atmospheres, which means that you're going to multiply by 1 atmosphere divided by 760 torr. All right, so that's basically the setup right there.
Yep.
And then the moles will cancel out here and here. The Kelvin will cancel out here and here. The torr will cancel out here and here. And the atmospheres will cancel out here and here. So
Yep.
again, you have to do the number crunching.
Yeah. I worked it out. It's okay. What's at 3 sig figs? It is 13.4.
13.4
liters.
liters. Okay, I'll take your word for it. Okay, so that's basically how that is done, all right? A bit more complicated than the previous example because you have to do some conversions. You have to convert from grams to moles, you have to convert from Celsius to Kelvin, and you have to convert from torr to atmospheres. And then you do the rest and plug the numbers in your calculator and get your answer. Oh, by the way, I just realized something. Actually, the final answer would have to be rounded off to 2 sig figs because of the, this right here, 720 is 2 sig figs. So that means it should be rounded down further to 13 liters. All right? Basically how that is done. All right? Any questions about this one? Any questions?
No, not for me.
Okay. I think this is going to be the last thing I'm going to discuss, and then I'm going to call it a day. So we have been introduced or reintroduced to the ideal gas equation, and we can actually use that equation to determine other things about a particular gas. For example, we can determine the molecular mass of a gas. Now, what we're going to do in order for us to know how to do this is that I'm going to introduce uppercase M as representing the molar mass of a gas, and lowercase m represents the mass in grams, right? So uppercase M is the molar mass, lowercase m is the mass in grams, all right? So if that is true, then the relationship between those two terms would be given as what you see on the screen here. The molar mass of a gas is equal to the mass in grams divided by the, I'm sorry, what did I just say? The molar mass, right? The molar mass of a gas is equal to the mass in grams divided by the number of moles, right? So you can rearrange this equation to give this, an expression for the number of moles. Moles of a gas is equal to the mass in grams divided by the molar mass, right? Now, the ideal gas equation can give you an expression for the number of moles. N is equal to PV over RT. So we have N equals to M, lowercase m over uppercase M, and N is equal to PV over RT, which means that this here will be equal to this. So we can set them equal to each other, right? And then we can rearrange to solve for uppercase M, and we get this expression. The molar mass of a gas is equal to the mass in grams times R times T divided by P times V, all right? So basically based on this equation here, you can calculate the molar mass of a gas. And there's an experiment that I haven't run that experiment lately, but I remember running an experiment for my students where they use this equation to calculate the molar mass of some unknown gases, and it works pretty well. So this is a very useful equation when it comes to calculating the molar mass of gases, all right? So based on that expression, we can solve this problem. What is the molecular mass of the gas? And it gives you some information here, all right? So let me turn on my pen here and let me proceed. So you're given a mass of the gas here. You're given a volume. You're given the pressure. And you're given the temperature. And the question is asking for the molecular mass, right? So the equation we're going to use is M, uppercase M is equal to MRT over PV, right? This is the molar mass, right? So we put the numbers in. So M is equal to 0.550 grams times 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 289 Kelvin, all divided by P. What is P? P, 0.968.
Let's see here.
I'm sorry, 68 atmospheres times V. What is V? 0.20 liters 200.00 liters. Okay, and in terms of units canceling out, the liters will go here and here. What else? Atmospheres will go here and here. Kelvin will also cancel out. So your final units would be in grams per mole. So again, I'm going to need your help in terms of crunching these numbers.
All right, I was working it out while you were explaining it, or I was punching the numbers in. It is 3 sig figs, so 67.4.
Okay, so the answer is, ooh, sorry. Okay, so you said the answer is what?
67.4.
67.4. Okay, now please note this is the molar mass, but the question is asking for the molecular mass, right? So the molar mass is the same numerically as the molecular mass, but the difference is that the molecular mass is expressed in AMU, so molecular mass is equal to 67.4 AMU.
Okay.
All right, and that would be the final answer. All right.
Cool.
Any questions?
No, I'm good.
Okay, so I think I'm going to stop here for now because it's 1:43. What I would recommend you do is that you try the next example and let's see what you come up with, and then we'll move on to other things. Also, before we end today's class, your next test or your first test will be next week. I'm going to post the answer keys for the quizzes that you have done so far in Canvas, so look out for that. And I'm also going to try to send to you guys individually your graded work, so that if you have any questions you want to ask, or if you want to review it for your test, that's fine. The only thing that's preventing me from doing that sooner than now is I have some scanner issues which I hope to have resolved by today. So look out for it. If not by today, definitely by tomorrow. I'll be sending you guys your graded work. All right. And I think that's all I have to say by way of announcements. Are there any questions you guys have?
Nope.
Any questions? Before you guys leave, let me make sure I take roll so that I have a record of your attending today's class. So let me get to my, today is the 10th. Okay, Arias Rios, Barber is here.
I'm here.
Cannon, not here. Chang, Chavis, Clark is here. DeGraff, not here. Franklin, I don't see Franklin. Han,
Here.
here. Panic, Aaron is here.
Here.
Holland, don't see Holland. Jurgensen.
Oh, Paul Holland is here.
Yeah, I'm here.
Oh, yeah, okay, thank you. Jurgensen, Rees, Rouse is here. Runnels is here. Santiago and Smith.
Here.
Is here. Okay, good. All right, so that's basically it. If there are no questions, enjoy the rest of your weekend, and I'll see you guys on Tuesday of next week. All right?
All right. Take care.
All right, take care.
Have a good one.